So I hope it's clear how we can find singular points of a function and how to classify the singular points. As I was mentioning before I started recording, I didn't include in the classification a type of singular points called removable singular points, but when they appear, they can just be removed. Basically, you can just change the function to be a function that is equal everywhere, but analytic at that point. So I'm going to assume that we can modify the function to always be analytic at a removable singularity. So for us, it's going to be more interesting to see what happens around typically poles. Also, well, it could be also essential singularities, but like real singularities of the isolated type. Okay, because those are what the type of points of a function that will let us calculate these contour integrals using residues. So let's start with, I think the last thing we saw last week, if I remember correctly, was the residue theorem. So let me repeat it here. So the residue theorem was telling us that if a function has sorry, just one moment. I know we didn't see it yet. So, but let's say it. Let's write it like this. If a function contains a finite number of isolated singularities, okay, let's call the location of these singularities, for example, Z0, Z1, Z2, etc. And all of them are, I mean, we are only interested in the singularities that are inside contour gamma. Okay, then the contour integral around that contour gamma of the function will be 2 times pi times I times the sum over all these singular points inside the contour of the residue of the function at each of these singular points. So here the notation is res, and then we have function and point, right? Phi zj, which means the residue of the function that corresponds to the singularity located at point zj. And so is this clear why? Because well, sorry, maybe not clear why. So last week we saw what happens if I have some contour. So I have any shape of contour going counterclockwise as usual. And we saw what happened if we have one singular point inside. Remember what we did was to break the contour a bit, maybe not so much, and then take another contour that avoids the singularity like this, right? And then this new contour doesn't have any singularity inside because that point is outside of the contour. So we found that the integral along the contour was the same as the integral, the clockwise integral around this point for any shape. So it is very easy to do the same if we have more than one singularity. You just need to imagine we have like 3 singularities located somewhere. So you can always take the new contour that avoids all of them like this, going through straight lines, circles, and then coming back. Okay, so going like in this direction, then coming back in the other direction. And again, when in the limit, when these the straight lines are taken to be closer and closer together, those pieces give a contribution of 0. And at the end, we'll have the sum of only the circles around. So this would be like Z0, Z1, Z2, etc. We'll have only the circles around the singularities, which are clockwise. So we will see that the sum of the total contour plus all these circles must be 0 because the function is analytic inside this contour where we remove the singular points. And the same that we did last week, because we changed from clockwise to counterclockwise, we can add the minus sign and change this sum equals 0 to the integral that we want equal the sum of the integrals over each of these circles, which, as we have seen, is we know the result is the same for any radius of the circle. So we can take the circle to be very small and do the Lorentz expansion in which all the terms are identically 0, except for the term B1, for the term B1 divided by Z minus Zj. Okay. So this is a bit more general version of the residue theorem. Just not, if you want to calculate this line integral around gamma, just need to find out what points are singular inside, and it doesn't matter if there are other points outside. We only want to know what happens inside the contour. We need to find these numbers. This would be one complex number at each of these points, which we call the residue at that point, the residue of that function at that point. And then we just need to add these numbers together and multiply by 2 pi I. That's all. Okay. So then the question now is, how do we find the residues? So remember, if we know the Lorentz series, let's remember what the Lorentz series is. So the Lorentz series of the function phi around, let's see. So for example, let's take the Lorentz series at Z0. Remember that the Lorentz series would just be some constant plus A1 Z minus Z0 plus, well, the normal Taylor series around that point. And then we'll have another constant B1 divided by Z minus Z0 plus B2 divided by Z minus Z0 square, etc. So even if we have infinitely many points, that would be for an essential singularity, or even if we have a pole for which the number of terms is not infinite, in every case, the residues is B1. So the residues of phi at this point Z0 is just this number B1, okay? The other coefficients don't matter for the calculation of the integrals. So let's see. So that's one way to find the residues. So we can find the residues of phi at one of these points, for example, very easily if we can write the Lorentz series. So well, this is not always the case, but this is if you know the Lorentz series of a function, then this would always be a possible way. And the method actually becomes a bit more complicated depending on the value of Z0. But this writing the Lorentz series is normally easier if you do it around the point 0. The point, I mean, if the point Z0 equals 0 is the singularity. Let me write here. This is easier if the singularity is at 0. What happens? So what if the Z0 is not 0? Then let's define a complex, another complex variable, which is complex variable minus the value of the singularity if the point is not at 0, and see what happens. So if we define this, we could find the Lorentz series as a function of delta, and then the coefficient of 1 divided by delta would be the residue. Okay, let's look at this example in these notes. What is the residue of the function sine z divided by z minus I squared at one of the singular points? Sorry, there is only one singular point. As you can see, the only point that makes the denominator equal to 0 is z equal I. You can see this should be a pole of order 2, right? But okay, actually, if you look at the Lorentz series of to find the residue using the Lorentz series, then well, there is this advantage that you don't really need to classify the type of singularity perfectly, because well, the type of singularity will appear when you find the coefficients of the Lorentz series, but you only need the coefficient of 1 over z minus z0. So what I was going to say. So to do this, let's define delta as here. So let's define delta as z minus I. Then the function sine z would be the sine of what? Well, we have to change to the new variable. So z is delta plus I, with delta the new complex variable. So if I want to expand the series of these, I need to find the series of sine z in terms of delta, and then divided by delta square to get the series of this function. Right? And well, dividing by delta square term by term is very easy. But what is this? What is the sine of delta plus I? Well, we need to find the, we need to expand this from the sine of the sum. And you can see that this will be the sine of delta times the cosine of I plus the cosine of delta sine of I. Okay, so we will have the sum of these two series. The series of the sine of delta, which we can write as delta minus delta q over 3 factorial plus delta to the 5, etc. All of these multiplied by the cosine of I, which you can go to the properties of the trigonometric functions and hyperbolic functions. You can see the cosine of I is the same number as the hyperbolic cosine of 1. And then for the cosine of delta, we can see there is I times 1 minus delta squared divided factorial of 2 plus etc. hyperbolic sine of 1. So we divide, so the sine of delta plus I divided by delta square is the function that we want to find the residue for. We just need to divide the all the terms one by one by delta square. So here we'll have 1 divided by delta, here minus delta divided by 3 factorial, blah, 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 hyperbolic cosine of 1. And the other series will have 1 divided by delta square minus 1 over 2 factorial, etc. Now you can see that the only term that is interesting for us is this one, 1 divided by delta, and the coefficient, this is plus, the coefficient of these would be just the number hyperbolic cosine 1. So so the hyperbolic cosine of 1 is the residue of the function at z equal 1. Is this clear? Anyway, in general, sorry. Fortunately, we don't have to find the Lorentz series every time we want to find a residue, because in some cases it is not as simple. Well, in this case, you can see the trick here, right? In this case, we know how to find the series of the sine of delta plus I because we know how to find the series of sine delta and cosine delta, and we know how to change from this to this. You can imagine there are a lot of cases where this type of trick will not work. Don't have to do that, especially if we know what type of singularity we have. We'll have a method that works very, very well at type of singularity. Let's start with the simple pole methods. If you have any question, please unmute yourself, because if you raise your hand or something, maybe I will not see it. So this is why I told you it's important to classify the singularities before we do anything. Because depending on the type of singularity, the method that you apply is a little bit different. So if you find that the singularity that you are calculating the residue for is a simple pole, then then you will notice that sorry, let me do something. Just one moment. Okay, sorry. So if you have the Lorentz series, I mean, remember what we want to do is to find B1. So imagine we don't have the Lorentz series. If we don't have the Lorentz series, then we will not see all these details of the function. But if we multiply the function by z minus z0, then it's easy to see that here we will have a0 times z minus z0 here. Here we'll have z minus z0 square. Here we will have z minus z0 cube, etc. You will have the powers plus 1, right? For this term, when we multiply by z minus z0, we just will have b1. For the next term, we'll have what? Well, the next term is 0 because it's a simple pole. So actually, for a simple pole, we don't have these terms. We have only one term, b1 over z0. So this function will be just this infinite series plus a number b1. So you can see the residues would be what you get when you take the value of this function at z equals z0. Okay, so we can write this just in case the point is still some kind of removable singularity. So we can take the limit when z goes to z0 of this function that is actually well behaved at that point, z minus z0 times phi. Because when z goes to z0, all these terms go to 0, right? And the only term that doesn't go to 0 is b1. And remember, this works because it's a simple pole. Okay, so it's important to know simple pole. Remember, simple pole b2 and higher are 0, so the series ends at b1. So this is the one simple way to find the residue if we have a simple pole. Multiply by z minus the singular point and just see what happens when z goes to that point in the limit. Not see what happens, but see what value this function takes. And this function should be analytic at that point because that's because it's a simple pole. And the complex number that the function takes is just the constant b1. Okay, so this is our first simple pole method. in many cases, the function is like the division of two analytic functions. So in that case, maybe it's also easy to rewrite this simple pole method in a bit different way. So if my function is, for example, a function p divided by a function q, and p is analytic, and q is analytic, but it has a zero, remember? It has a simple zero, so that phi has a simple pole. So in that case, remember, the function q has a simple zero, then we can write q to be just the product of z minus z0 times another function r that doesn't have a simple zero, that doesn't have a zero, that is different from zero at that point. Okay, so if you can find r, if you can find that that r in a convenient way, then you can see that the residue of function phi at this point will be just the value of p at z0 divided by the value of r at z0. And it's very easy to see why, because, well, q is r times z minus z0, so z minus z0 times phi will just be p divided by r, and take the limit when z goes to z0 you don't need to take the limit because both functions exist and are analytic at z equals z0 and are not zero, so you can just divide these two numbers and you get the residue. Okay. In some cases, okay, well, we can see an example of this. So can I do it here? So example, let's find the residues at each of the simple poles of this function. So imagine my function is z divided by z plus 1 times 2z minus 1. Okay, where are the singularities of this function?
-1 and 1/2.
Yes, that's correct. And you can see that both of these are simple poles. Okay, so if you don't remember why, just notice that you can see that how they are simple zeros of the denominator. If you multiply by well, in this case, if I multiply this function by z plus 1, I get a function that is not singular at z equal -1. So these are two simple poles. So we have simple poles at -1 and 1/2, right? So, well, sorry. So in this case, it's very easy to apply this equation. What is p? So here, for the first singularity, z equal -1, well, we have p is z. So, okay. So let's apply it directly. So here we can say residue of phi at minus 1. We can write it like this, the residue of phi minus 1, and we can write it as p of minus 1, which is minus 1, divided by r of minus 1. What is r? So notice that r is defined here. It will be the part of the denominator that you get when you separate it as z minus z0, in this case z plus 1, times something else. So that something else here is 2z minus 1. So we have 2 times minus 1, minus 1. Right? And we get minus 2 minus 1 is minus 3. So here we have 1/3, right? That is the residue. And for the other point, the residue of this function at the point 1/2. What will we get? Well, I get, again, p, the numerator is just z, so it will be 1/2 in the numerator. And then the function r here is a different function r, of course, is, again, what you get when you you have to kind of divide q, the denominator, by z minus 1/2. So notice here, this here is not z minus 1/2, but it's 2z minus 1, which is 2 times z minus 1/2. So you have to take that into account. Is we are doing kind of factorization here. So you have to notice that z plus 1 times 2z minus 1 is the same as z plus 1 times 2 times z minus 1/2, right? So if you want to write it like z minus 1/2 times r has a 2, okay? So that 2 is important. Okay, let me remove this first. It's a bit messy. So we have, here we'll have r, which is z plus 1, 1/2 plus 1 times 2. Okay. So here we have the denominator 1/2 plus 1 is 3/2 times 2 is 3. We have 1/2 divided by 3, which is 1/6. Did I do it correctly?
Yeah, it's correct.
Thank you. Do you have any question? So finally, for the simple poem method, sometimes we don't see that that function r directly. Let's say if q, the z cannot be expressed as z minus z0 rz easily, then we can use L'Hopital. Right, L'Hopital's rule. Remember L'Hopital's rule for the limit of an undetermined, in this case would be 0 divided by 0 type of limit. L'Hopital tells us that the limit of the functions is the same as the limit of the derivatives of the functions. But here, since we are using, I mean, you can just use it like that and go to take take this function residue, sorry, take this with this function. Remember, our function phi is p divided by q, and just take that. But actually, for this specific case of finding the simple pole residue, after you apply L'Hopital, you will always have the same type of simplification. So you can just put this in the method directly, so you can apply directly. The idea is that the function 0 divided by 0, the function that have zeros, will look like this. Remember, we are taking the limit of z minus z0 times phi, and phi is p divided by q. So really the 0 of the numerator comes from this term, right? Because p is not 0 at that point. P is not 0. So here we have z minus z0, and q is also 0, so that's why we have 0 divided by 0. So when we take the derivatives independently for the numerator and the denominator and evaluate them, or take the limit when z equals z0, the value should be the same according to L'Hopital. So what is the derivative? The derivative with respect to z of this product, z minus z0 times pz. Well, the derivative of q will be a function q prime that, if you remember what we discussed before, the derivative of q is not going to be 0 at that point. Why? Because remember, if the derivative of the denominator is also 0 at that point, then that is not a simple 0 of q. That would be a 0 of order 2 or more of q. So if we know z0 is a simple pole of q, then we know by the definition of simple zero, not simple pole. It's a simple pole of phi because it's a simple 0 of q. By definition, we know that the derivative at that point is not 0. Okay. So what is the derivative of this part here? Well, we just need to see, as usual, derivative of the first term, which is 1 times p. Okay. Well, let's write it here. So z minus z0 times p will be 1 times p plus z minus z0 times the derivative of p. Okay, so if I put this sum in the numerator, we can see that when z goes to z0, here we'll just have the function p evaluated at z0. And this will have a limit of 0. Because, yeah, so the limit when z goes to z0 of this will be 0. So that term always disappears. So we only have this first term. And the derivative of q at z0, which, as I told you, is not 0. So this is a number that we can define. Okay, so basically this goes to p of z0 when z goes to z0. So okay, you can just start with the function and apply L'Hopital to the limit, etc. But it's easier if you realize that you will always have something like this, in which remember, the function phi is p divided by q, but the limit of z minus z0 times phi will be p divided by derivative of q. So p doesn't have derivative, but q has the derivative. This is because we are not taking the limit of function phi, but the limit of phi multiplied by z minus z0. So you will always have the same numerator as the function phi evaluated at the singular point divided by the derivative of the denominator evaluated at that point. Again, because we know that derivative is not zero. Let's see an example. Do you have any questions?
Sorry.
Yes.
Why is C0 is a simple zero of Q again?
Yes. That was one property of simple poles that we mentioned last week. So if so here we are assuming P is analytic. So I'm assuming phi is the division of two analytic functions. P is analytic, Q is analytic, but Q has a zero. So the points where Q have a zero will be singular points of this function phi. But we saw that if Q has a simple zero, then this function has a simple pole. And if Q has a zero of order 2, then phi will have a pole of order 2, etc. Of course, always assuming, we are assuming that P of the 0 is not 0, and P is analytic at that point. And Q is also analytic, but it has a 0. This is something that happens a lot. So we are assuming that. When did we mention that? Yeah, when we define the order of a 0 and the order of a singularity, we found that is it clear? You remember now?
Yeah.
So,
thank you.
Yeah, thank you. So these are simple pole methods. So I know the point is a simple pole of phi. And as I say, if P is analytic and P is not 0, that's very important. Did I mention that? So let me write it here. P at z0 is not 0. So if Q has a simple 0, then phi has a simple pole, which is the case that we are considering. We are considering this is only true for simple poles. For example, what is okay? I have this note. So sorry. So imagine my function of interest is the exponential of minus AZ, sorry, hyperbolic secant of Z. Well, this function doesn't look like P over Q until you realize that the hyperbolic secant is actually the same as 1 divided by the hyperbolic cosine. Then it is very clearly a function P over Q in which P and Q are analytic actually at every point. Remember, the hyperbolic cosine is the sum of exponentials. So if the exponential is analytic, the hyperbolic cosine is also analytic. If we don't include infinity, of course, we are not including the point at infinity. So these are analytic everywhere. So the singular points come from the zeros of the denominator, the zeros of hyperbolic cosine. And we have already discussed, right, those singular points. There are infinitely many singular points of this function because hyperbolic cosine has all those zeros. So let's take one of them. Let's take pi over 2i. This is one point where the hyperbolic cosine is 0. And it is possible, it's very easy to check that it is a simple pole because we can find that it is a simple 0 of hyperbolic cosine. Remember, one easy way to check that it's a simple 0 is to see if the derivative is 0 or not. The derivative of the hyperbolic cosine is the hyperbolic sine. And when you calculate the hyperbolic sine of this, you will find that it is not 0. So yes, this is a simple pole of phi. So here, as I said, if you just notice how the simple method is already simplified using L'Hopital, you can just apply this formula P divided by Q prime. So in this case, so you have the residues of phi at this point, pi over 2i. This will be the function of the numerator without derivative, so exponential of minus az, exponential of minus a pi over 2i, divided by the derivative of the denominator. And okay, you should remember that the derivative of the hyperbolic cosine is the hyperbolic sine. Okay, evaluated at this point. Okay. And then we just, well, we just get a number that we can simplify it a bit by noticing that the hyperbolic sine of a purely imaginary number, pi over 2i, is just I times the sine of pi over 2, which is not 0, okay? Sine of pi over 2 is 1. And the exponential here, let me write it as minus I a pi over 2. Well, it's here a can be anything, so we cannot simplify it more, but notice that this exponential is just like a number on the unit circle with, well, sorry, if a is real, okay, never mind, a doesn't need to be real, right? So we don't know what this number is, but we cannot simplify it more. But here, this will be that number divided by I. Okay, we can leave it like this. This will be the residue at that point. As you can see, it's very easy, but notice that this simple pole method can be applied directly if we remember that how L'Hopital rule simplifies this case where we have z minus z0 p divided by q. And note that this L'Hopital method can even be used, can use in any case, even if this q can be expressed as this, even if we know how to factorize q, really the method that uses L'Hopital would still be valid. We could still use this method. So okay, let's see this other example. I think it's interesting. Note that okay, let's call this method residue of phi z0 equal P of z0 divided by Q z0 is also true even if Q is Z minus Z0 R. So even if we know how to factorize Q, we can sometimes use this method and things would be easier. So in this example, if I want to find the residue of cosine Z divided by 1 minus Z to the fourth. Okay, so we want to find the residue. As you remember, this denominator has 4 zeros. The 4 points where Z to the power of 4 is equal to 1, which are 1, minus 1, I, and minus I. Okay, let's focus on Z equal I. That is a simple pole. So these 4 zeros are simple zeros of 1 minus Z to the fourth. So when we divide by that, we get 4 simple poles. And the cosine, again, the cosine is analytic at all of these points. Also, the cosine at I is not 0. So then here we can take P of Z to be cosine and Q of Z to be 1 minus Z to the fourth. So if you factorize one, let's see. So if you factorize what we call Q, 1 minus Z to the fourth, in terms of the factor, so we could write this as, well, we would need a minus side minus Z minus 1 times Z plus 1 times Z minus I times Z plus I. This would be the factorization of this polynomial. If you do this and apply the method, this method here, P divided by R, well, you will spend a few minutes simplifying the division of complex numbers. We'll have, so only Z minus I will disappear. You will still have to evaluate I minus 1 times I plus 1 times I plus I, etc. But however, if you find the derivative of Q, you notice that the derivative of Q is just minus 4Z cubed, which is much easier to evaluate. So the residue could be found in either way, but in this case, it's easier to do it as this, as P divided by Q prime, or cosine of I divided by minus 4 I cubed. And the result, of course, the result it has to be the same if you do it in one way or the other, because the residue is just one number. But this way is so much easier or faster. Notice that I cube is minus I. Cosine of I, again, you can simplify to hyperbolic cosine of 1. And I cube is minus I, so have that divided by 4I. You can do it in one step. You can do it the other way, but it will take a bit more effort. Any question?
Teacher, why not have singular point at 1 minus 1?
It has. I'm just sorry. I'm just calculating one of them. Okay.
Oh, okay.
Actually, it will be very similar. So there are 4 singular points: 1, minus 1, I, and minus I. But this is an example for one of them. The other 3 would be very similar. Just of course, each point has its own residue. If you calculate it for other points, so you will get a bit different numbers, but will be calculated the same way.
Oh, okay.
So
And,
there are 4 singularities here. Yes.
and you say it's simple pole, right? But I remember a simple pole have only one point, right? But
No, well,
but
what do you mean?
you say first. You say first.
Sorry. A function can have more than one singularity, and then each singularity could be any type of pole, or I mean, here this is a function that has 4 isolated singularities that are for simple poles, because the denominator, which is this function q, has 4 simple zeros, the values that make this function equal to 0, right? Sorry, what was your question? So you can see, yeah, the factorization makes it easy to see. If you substitute here z equal 1, z equal -1, z equal y, or z equal minus I, sorry. In all these cases, the function q is 0, and the function cosine divided by that is singular at these 4 points. Okay, so there are 4 singularities like this, and they are simple poles because, well, you can see how if you multiply by z minus I, for example, then this term will cancel, and the other terms are not 0, so that's another way to check that that is a simple pole. But yeah, as I said, you can also check that these are 4 simple zeros of q.
Oh, okay, sure.
Thank you. How are we doing? What time is it in Thailand? Sorry. Okay, let's take a break here. Okay. Sorry.
Sorry.
Yes.
I think I gonna ask. Let's go back to second page on at the end of the page.
Yeah. The second page is.
Yeah.
Oh,
let me think about it.
So yeah, well, this is an example of. I mean, we didn't see any step-by-step way to find the Lorentz series, so we just need to use whatever we know from real variable. So there are a lot of things that we will not know how to do, but we know how to do the series of the sine, the series of the cosine, the series of the exponential, things like that. So this is an example where you could use your knowledge on Taylor series to find the Lorentz series of the function. Is that your question?
Oh, no. My question is, for this example, c equal to I is the whole is the singularity of this example, right?
Yes.
But this singularity is a pole of order 2, right?
Exactly. Yes.
Then why the residue is not hyperbolic side on the
yeah, very good question. So remember, that is a very nice thing of the residues. So the residues is always the coefficient of the term 1 over delta. for any order, for any see, pole order. So it doesn't matter that so here the term of 1 over delta square will be like B2 in our equation here. Have B1, B2, B3. We could have infinitely many coefficients, but the residue is always coefficient B1. It doesn't matter what is the pole order. I'm not sure if this is clear, or the type of pole. Or the type of singularity. If the singularity is isolated, we will always want to find the residue to be the coefficient B1.
Oh, because of last week we proved that the residue of anything is just equal to B1, right?
Yes, because remember we saw how if you do the integral around a circle, all the terms for the Lorentz series give you a total integral of 0 because you are integrating around a full circle, except B1. B1, when you integrate around that circle, it just gives you the number B1. So that's why the residue is important, because the value of the integral for all the function, the total function, is just the same as the value of this function B1 divided by z minus z0, that term only. And this number B1 is actually the number that you get for the integral, and is what we need to calculate integrals next. So yes, remember, always, it doesn't matter if, so for example, here you have B2 that is not 0. That means this is not a simple pole. It doesn't matter. We always want B1. B1 is the one, the coefficient of 1 over delta, which in this case was hyperbolic cosine of 1. We will always want that. That is the definition of residue for every isolated singularity, not only simple poles, okay?
Oh, yeah, thank you.
Okay, thank you. So if you don't mind, yeah, if you don't mind, I would like to take a break until what time is it? So, okay, we already know how to find the residue of any function on a simple pole. Right, I mean, we have seen three different methods, but it's just the same method that can be applied in 3 different ways. In the end, we just want the coefficient B1 of the Lorentz series. What happens if we have a pole that is not a simple pole? Okay. Let's see. Let's take this Lorentz series again and see what happens. Sorry. So remember, we always want the coefficient B1. Now, if the function has a singularity that is not a simple pole, but it is a pole of higher order, then you will notice that there will be more terms here. There will be more terms here that are not 0. In that case, what we were doing for the simple pole doesn't really work very well. So notice that if I multiply this function by z minus z0, then the function still will have a singularity because of the, for example, term B2. Okay, let's imagine let's imagine that Z equals Z0 is a pole of order 2, for example. In that case, the Lorentz series will just have B1 over Z minus 0 plus B2, and that's all. No more dot dots here, okay? And we know B2 is not 0, because if B2 is 0, then we have a simple pole, right? But we always want B1. So that means that if I multiply the function by, for example, Z minus Z0 square, okay, if I multiply this function by Z minus Z0 square, then what I get is not what I want. This function, when Z goes to Z0, will go to the number B2, which is not the residue, okay? B2 is not the residue. The residue is always B1. So we cannot do it as simple as that. But notice that if I take the derivative with respect to a Z of this thing here, Z minus Z0 square V phi Z, then we can, well, sorry, let's write here what this Z minus Z0 square phi Z would look like. This will be A0 Z minus Z0 square plus A1 Z minus Z0 2 plus 1 3, etc. Then we will have the two terms that have the denominator will be B1 divided Z minus Z0 times Z minus Z0 square will be B1 times Z minus Z0. And then the term B2 divided by Z minus Z0 square will just be just B2. Okay. And as I said, these, I can take the limit when Z goes to Z0, but then I get the number B2, which is not what I want. But if I take the derivative first, then what would I get? But just let's do it term by term. The first one will be A0 times 2 Z minus Z0. The second one will be A1 times 3 Z minus Z0 squared. This is the derivative of each polynomial term. Then the term B1 Z minus Z0 will just be B1. That is the derivative. And the derivative of the constant B2 will be 0. Okay. So these would correctly go to B1 when Z goes to Z0. And that is what we want. So that would be a possible way to find the residue if the pole has order 2. Okay. Let me see. Now, well, since I can copy paste, then maybe we can just do it for, let's do it again for order 3. But you can see how it's going to be. Just, oops. You can see where this is going, right? So for example, now if I have a pole of order 3, then I will have another term here, B3 divided by Z minus Z0 cube. And then B2 can be anything, but B3 is not 0. And let's see, in this case, if we do it like this, again, it doesn't work because we will have here a term that depends on B3. If I multiply, however, by the cube of z minus z0, then what would I have? I would have here, this would be 3, this would be 4, etc. This would be square. B2 will have z minus z0, and we'll have B3. The derivative of this, again, let's do it term by term, would be 3 square here, 4 cube, etc. But now we'll have derivative of this will be 2 z minus z0 plus b2 plus 0. Again, this is not helping, but if I take the derivative of this again, so if I take the second derivative of this, z minus z0 cube phi z, I just take the derivative of the derivative, and then you will see, again, the positive terms are not very interesting. We have a 3 times 2, 6, z minus z0, a1, 4 times 3, 12, z minus z0 square. But now, when I take the derivative of b1 times 2 z minus z0, I get 2 times b1. And the derivative of b2 is 0. So I could, if the pole is order 3, I could just multiply by z minus z0 cube, take the second derivative, and find the limit of that and divide it by 2. Okay. Well, in general, we can get this, what we call the multiple pole method, which to do the multiple pole method, we need to know roughly the order of the pole, although it's kind of flexible. But anyway, so let's write it like how it works in general. So if Z0 is a pole, imagine we know exactly the pole is order n. Then to find the residue, B1, we just take the function z minus z0. And here, if you look at our derivation before, it looks like for order n, we will have z minus z0 to the power of n, right? But actually, if we multiply by another power, this still works as long as m is at least n. So if m is larger than n, this would also work. For example, if my pole is order 2, I could do it like this, right? Multiply by z minus z0 square and take the first derivative. But actually, if the pole is order 2, imagine if B3 is 0 in this case, but B2 is not 0, then you can see taking z minus z0 to the power of 3 and taking the second derivative, still, it doesn't matter if B2 and B3 are 0. Still, it gives me this 2B1 when I take the second derivative and the limit. So that means I can take any power m that is at least equal to n, multiply by the function, and then they take the derivative of this. But the derivative has always needs to be the m-1th derivative. So the same number m that we choose minus 1. Okay, so if you put a power of 3, then the second derivative. You put a power of 4, that had to be the third derivative. And finally, to get the correct number, you see, for example, here we have to divide by 2. If you take another derivative, you will have to divide by 6. So in general, you will have to divide by the factorial of this number, m-1. And take the limit of this. But the limit of this function is analytic, so the limit of this is just evaluate the function at z equals z0. This is the most general way to find the residue of a function phi on a pole of any order. Actually, the simple pole method is a special case of this. But notice that we also have this flexibility of taking a power here, m, that is not, doesn't need to be equal to n. Can be equal to n, but it could be larger, and the result will be exactly the same. That gives us a bit of flexibility that will make it, well, in some cases you can choose a value of m that makes the calculations a bit easier. And the result would be always the result of this derivative of this function will always be the factorial of m-1 multiplied by the coefficient b1. Okay. Did anyone say something? Okay, if you have any question, please speak up. I cannot see the... Okay, so let's see this example. Let's find the residue of sine z divided by z minus pi cube at z equal pi. Okay, what is the type, what is the singularity at z equal pi? What do you think? What type of singularity is this?
Order 3, right?
It looks like a pole of order 3. Actually, it's a pole of order 2. And the reason is because this will be the zero of the denominator would be, the order of the zero of the denominator is equal to the order of the pole if the numerator is not 0. The problem here, the numerator at z equal pi is also 0. So you have to well, see what happens when you multiply this by z minus pi square. And when you multiply this by z minus pi square, you get that, well, what before they was mentioning, it can be called a removable singularity, but you get something that has a limit. So actually this is a pole, this is a pole of order 2. And you can also, how do we see this? Well, of course, the Lorentz series doesn't have term divided by cube, because if you divide the series of the sine around pi by z minus pi cube, you only get a term divided by z minus pi square. So it's pole of order 2. Did we see something like this? Well, anyway, if it's a pole of order 2, that means we can apply the method for n equal 2. That means m can be any number that is 2 or larger. So normally you will think the smaller would be the better, right? So we could take m equal 2. In this case, the residue of this function at pi would be, just substituting, we have 1 divided by the factorial of 1, which is just 1. And then we'll have the first derivative of z minus z0, sorry, this will be pi, z minus pi square times phi, evaluated at z equal pi. Now, if you do it like this, you will have the derivative of the sine of z divided by z minus pi, which is okay, but it's a bit longer than if you use m equal 3. So this is a case where taking m equal 3 makes the solution a little bit easier to find, even if you need to find a second derivative. If m is 3, here you will have 1 divided by 2 or 2 factorial. Okay, let's write it explicitly. This will be 1 divided by 1 factorial. This is 1 divided by 2 factorial, which is just 2. And here you have to find the second derivative of this function, which you think, okay, second derivative takes more work, right? But actually, the function z minus pi cubed times phi is just the sine of z. So this is 1/2 of the second derivative. Oh, well, and then evaluated at pi. The second derivative of the sine of z, evaluated at pi. And well, the derivative of the sine is the cosine. The derivative of the cosine is minus the sine. So this is just minus the sine of z. 1/2 of that evaluated at pi. Okay, let me just write it directly. Minus the sine of pi divided by 2, which is 0. Okay, the residue can be 0, of course, if the pole is not a simple pole. If the pole is a simple pole, the residue cannot be 0, because the definition of simple pole is the Lorentz series has a B1 that is not 0, and the residue is B1. But if the pole is order 2 or more, that means there are higher order coefficients, B2, B3, or whatever, and there is no condition on B1. B1 can be any number, any complex number. So in this case, it is 0. Okay? As you can see, just choosing m equal 3 is a little bit easier. If you do it in the other way, the result should be the same. We need to find the derivative of sine divided by z minus pi, which, okay, it's not a big deal, but just to show you that this gives a bit of flexibility. Any question? Should we check these examples? Let's check some examples. Okay, what do you think about this function? If I want to find the residue of the function 1 divided by z squared plus a squared at the point IA. Okay. What method should we use here? So of course, normally we need to find the singularities and then choose the singularities that are interesting for us, and then calculate the residue. Now here we are doing just the last step. We know, I mean, I'm telling you, IA is one singularity. There could be more, okay? There are more, but IA is one of them. And I want the residue at this specific singularity. So the thing now that we need to do is to decide what method to use, which depends on the type of singularity. So what do you think? what do you think? What type of singularity you think I multiplied by A is? Let's assume A is a real number. What do you think? What method should we use here? Sorry?
Simple poll.
It's a simple poll, right? Does everyone understand why? Or does everyone remember how we could check that this is simple poll? Because you could also just test there. I mean, there are not a huge number of possibilities, right? So okay, in case, if you want to check it, remember, here we are dividing an analytic function by another analytic function. So we are interested in the order of the zero of z squared plus a squared. And z squared plus a squared at z equal ia is minus a squared plus a squared, which is 0. However, the derivative of this function is 2z, which at z equal ia is just 2ia, which is not 0. That means this number is a simple 0 of the denominator. That means the numerator is not 0 also, it's analytic and not 0, so that means a simple 0 becomes a simple pole of 1 divided by this. Okay. So if this is a simple pole, then we should just choose one of the 3 possible simple pole methods, right? Which one is better here? Well, they are very similar. Do you want to choose one? So remember, we have 3 equivalent simple pole. So simple pole method. We have 3 equivalent ways to calculate it. The limit of z minus z0 times phi when z goes to z0, or p of z0 divided by r of z0 if phi is p divided by q and q is z minus z0 times r, or p of z0 divided by the derivative of q at z0. Again, if phi is p divided by q and p of z0 is analytic and not 0. Which one do you want to try here?
Last one.
The last one is a good choice. So let's see here, p is 1, and then the derivative of 2z, sorry, of z squared is 2z. So yeah, this would be the easiest, right? So we have p divided by the derivative of q evaluated at z equal ia, so it's 1 divided by 2ia. Quite easy, right? Now we remember this. Let's see another example. And for your assignment, you can also try some of the singularities of the previous homework. Another example, what is the residue of 1 divided by z squared plus a squared squared? One of the singularities is also at ia. What type of singularity is this?
It's a pole of order 2, right?
Yes, this would be a pole of order 2. And again, you can check it by noticing that it's a 0 of order 2. So this one is 0 at ia, and the derivative of this, which is 2 z squared plus a squared times 2z is also 0. The derivative is also 0 at IA. But the second derivative is not 0. You can find it. Anyway, so it's a pole of order 2. That means we need to use the multiple pole method, okay? Remember, multiply by a power of z minus z0, and then take derivatives m minus 1 times. So what is m here? So we know n is equal to 2, a pole of order 2. And here I will guess equal to 2 is also the easiest thing. Do you agree? So the case m equal to 2 is quite easy because the factorial is 1 and the derivative is just the first derivative. So we'll have 1, the derivative with respect to z of z minus ia square multiplied by z square plus a square square. Take the derivative first, then evaluate it at z equal ia. Okay, let's do it. Do you agree with this? This is just a simple multiple pole method with m equal 2. Let's see, what is the derivative of well, actually, we could also factorize the denominator. But okay, let's find the derivative of this. Derivative of numerator times denominator minus numerator times derivative of the denominator. If I made some mistake, let me know. Divided by denominator square. Wow. Anyway, there may be some easier way to do it, but actually, if you will notice that for example, here everything becomes 0 at z equal ia. But if I multiply, if I can see something cancels here. What did I do wrong? So okay, here I have 0 times 0 minus 0 times 0. And here divided by 0. Okay. Well, let me simplify this a bit. So we'll have the first term will be 2z minus ia divided by this thing square. The second term can be z minus ia square 2 4 divided by z square plus a square cube. Everything is 0. But Yeah, well, this is like taking this square times this to the minus 2, the derivative would be like this. Now, okay, sorry, there may be some faster way to do this. How would you do it? Okay, maybe it's easier if we just factorize the denominator. Notice that z squared plus a squared. Sorry, this is the product of z plus ia times z minus ia, right? The sum times the difference is the difference of the squares. The squares ia is minus a squared. So if I take this squared, this will be this squared times this squared. So that means this thing here is just this. Okay. So yeah, simply this would be the derivative of, this saves a lot of time, the derivative of z plus ia squared, okay, evaluated at ia, and this would be 2 times z plus ia. Evaluated at ia, so it's 4 times ia. Sorry, no, I did something wrong. Sorry, this was z plus ia squared. This one. I'm getting a bit. Sorry, I forgot. This was in the denominator. Okay, sorry. This is the derivative of 1 divided by z plus ia squared. Okay, now, yeah, this is minus 2 divided by z plus ia. Right. Okay, and now evaluated at ia gives me minus 2 divided by ia plus ia 2. No, again, what did I do? Minus 2. Oh, no, sorry, this has a minus 3. Sorry. Minus 2, this to the minus 3. So we have 2ia cubed. Okay, the result is minus 2 divided by 8, which is 4. I cubed, which is minus I, so this plus, this disappears, and then a cubed, right? Yeah. Okay, this is what it should be. Do you want to try one? Maybe you are more efficient than me. Okay, let's try this one in the list. The residues of the exponential of az divided by 1 plus az. The denominator has a lot of zeros. Okay, so one of them is I pi. The numerator is not 0 at I pi. So what type of What type of method should I use here? What do you think? What type of singularity is IPy here? All right, let's check again. The exponential of IPy is -1, right? So that means the denominator is 0. But the derivative of the denominator is -1 because the derivative of the denominator is the exponential of z. Evaluated at IPy, it's -1, as we are saying here. So this is a simple pole, right? So let's use a simple pole method. Now remember, in this case, Q is 1 plus the exponential of z, which is not clearly, I mean, we cannot easily express this as, as z minus IPy times RZ, right? There is no obvious function. The only function will be 1 plus the exponential divided by z minus IPy, which doesn't help. So in this case, there is only one method that would work, and that method would be the one based on L'Hopital. So this is a simple pole, and then we just need to find the numerator without derivative, evaluated at IPy, divided by the derivative of the denominator, which is the exponential of IPy. Do you agree? And since the exponential of IPy is just -1, this will be just minus the exponential of I times APy. The last example, you like to try this? Cosine z divided by 1 minus 2 times sine z. What do you think about this? Well, I'm telling you, one singular point. Again, this one has infinitely many singular points. One of them is pi over 6. Because the sine, what is the sine of pi over 6? What is the sine of pi over 6? What is supposed to be 1/2? Is this correct? Pi over 6, which is okay. So the sine of powers, oh no, sine of pi over 6. Sorry. Yeah, of course, it's 30 degrees. So the sine of 30 degrees is 1/2. That's why the denominator is 0. Okay. What is the cosine of 30 degrees? Well, whatever, square root of something is not 0. Okay, so the numerator is not 0. The denominator is 0. Is it a simple 0 or something else? Who can tell me? Pi over 6. What type of singularity is pi over 6? Well, I guess
it's
you already.
simple.
Yeah, it's a simple 0. Sorry, a simple 0 of the denominator. So yeah, it's a simple pole. Notice the derivative of the denominator is just -2 cosine, -2 times the cosine, and the cosine of 30 degrees or of pi over 6 is not 0. So yeah. So this is a simple pole. Again, we don't see this as p divided by r z minus pi over 6. So we can use the L'Hopital. For the L'Hopital, again, we have cosine of pi over 6 divided by the derivative, which is minus 2 times derivative of the sine is the cosine, evaluated at pi over 6. So actually, it doesn't matter what the value of cosine of pi over 6 is here, because they cancel. We have minus 1/2. Okay. Okay. So today we want to start applying these calculus of residues to some interesting applications. So let's use this method to evaluate some integral. We are going to evaluate only definite integrals. Remember the difference, right? Indefinite, if I say indefinite integrals, indefinite, that would mean I take a function and I find another function that has a derivative equal to the first function for any value of the variable. Now, we don't want indefinite integrals, we want definite integrals, which is just I take a function and very specific limits and calculate the integral between those limits. So notice this thing is going to be useful in general for integrals of the real variable, but we are going to use complex variable to find the integral more easily. Okay, this is going to be the topic of not only the rest of the class today, but also next week class. Okay, we are going to see several examples where we convert somehow a real variable integral with definite limits. The limits could be 0 to infinity, or they could be, well, there are some cases of interest, but definite. They have to, they cannot depend on a variable. And we will convert these real variable integrals into a contour integral of some function in the complex plane. And remember, the contour integral can be easily calculated or converted into a sum of residues based on the residue theorem. Okay, so let's start with what happens if you have an integral, a real integral, okay, of this form. I have a function capital F that depends only on the sine and cosine of the variable. Okay. And I want to integrate the variable around a full circle. So the definite limits are some angle phi and phi plus 1 full circle to pi. So, well, phi could be 0, could be minus pi, or any, it doesn't matter, because when you do the, you evaluate the function around the circle, the function is going to be periodic. So it doesn't matter where you start and you end. The important thing is you do the full 2 pi radians. The function is periodic because, notice, it's some function of the cosine and the sine, okay, which are periodic. In some cases, well, of course, if this function can be evaluated in a simple way using normal methods, separation of variables or change of variable or whatever. Sorry, separation of variables, I mean integration by parts or change of variable in real variable. Sometimes it's easy to do like that, but in some cases, it is easier to use a complex variable and convert this function into a complex variable function. Okay, for example, in the case where you have some powers, or like some powers of cosine and sine divided by other powers of cosines and sines added together. Some of these things can be difficult to treat in the real variable, but we can convert in a simple way into a complex variable by imagining this: the variable theta of my integral is the argument of a complex number. Okay, so it's kind of doing a change of variable from the real variable theta to the complex variable exponential of I theta. Okay, so remember, the exponential of I theta is also cosine theta plus I sine theta, right? We see that also differential of z would be just the derivative of the exponential. Here, this is I exponential of I theta, differential of theta, right? Now, using these things, and using, of course, remembering that the cosine square plus sine square is equal to 1, we can do a change. We can change from theta to z just by substituting. Noting the cosine of theta can be written as z squared plus 1 divided by 2z, for example. You can see it like this. The sine of theta can be substituted by z squared minus 1 divided by 2iz. And from this, you can see that d theta is going to be minus I dz divided by z, right? Because notice this is z. Sorry, this looks like a division. That, I mean, this thing here is just z. Okay, so putting these things into this integral, then what do we get? Well, notice that for the integral of interest here, we will have, so imagining theta is the argument of a complex number, then this complex number will just go around this circle on the complex plane, right? And if I call this circle, normally we call gamma the contour, but for a circle, let's call it C. If I call this contour C, then we can use the residue theorem to convert the integral of the real variable theta into a contour integral for the complex plane Z. Well, so okay, I can give you the full equation by substituting these things in this equation, but it kind of doesn't, in my opinion, okay, it kind of makes sense to just do the transformation in each case. But just so you know, well, the first thing is the value of phi is going to be not important. So if you start at any point, if you start at any point of the value of theta and go 2 pi radians around the circle, the result is going to be the same. So actually, the value of this integral is always going to be the same as the value between 0 and 2 pi of this, okay? And as I said, you can change this into a contour integral over the circle C. Let's see, where you evaluate the function f at the values of, instead of cosine theta, every time there is a cosine theta, you evaluate it at z squared plus 1 divided by 2z. Every time there is a sine theta, you evaluate it as z squared minus 1 divided by 2iz. And you multiply this function also by minus I divided by to calculate the integral because of the d theta. So this integral will have the same value, but this integral can be found using the residue theorem. The important thing is that the function is going to be this, including the 1 over z. Whatever this function is, this function will have some residue, some singularities. And remember, from the residue theorem, we only care about singularities inside the contour. By the way, this circle has radius 1, because notice the value of z here has modulus 1. So this is the unit circle. We call this the unit circle. Okay, it goes through 1, it goes through minus 1, goes through I, and minus I. Okay. So we just need to see what singularities of this function, including the 1 over z here, are inside the unit circle or have a modulus less than 1. The singularities outside don't matter at all. They don't contribute to this contour integral. Okay, so using the residue theorem, this could be expressed as, well, let me write it here, 2 pi I times the residues of this function that are inside the unit circle. Okay, so let's say modulus of these numbers are less than 1. And well, we could also take the minus I, can take this minus I out of the integral, and that will mean we just have, I mean, we could simplify this equation a bit, but doesn't matter too much. But okay, if I take the minus I out of the integral, it will cancel this I times minus I equal to 1. So we'll have 2 pi without the I, and now the sum over this these singularities, and the function of interest is just 1 over z times f evaluated at z squared plus 1 over 2z, z squared minus 1 over 2iz. Okay, let's see some example. But as I said, this equation, well, you could just substitute here, but in practice it's okay to just do it step by step. One of the tricky things here is to decide what singularities, or find all the singularities of this function, including the 1 over z, and find which of these singularities are inside the unit circle, and then find the residues using the methods that we have seen today. Once you do that, you just have to add these numbers together. and you get the integral. Let's see some example. Is there any question about this? So I have this example here. Let me call the integral of interest I. It's a definite integral, so it should be a number. Now, one trick that is also interesting to notice is that I start with a real variable integral. Okay, I'm going to assume a plus sine theta in the denominator, but I'm going to assume a is real. A is real. I'm going to also assume that a has an absolute value larger than 1. Okay, here this is absolute value because a is real. But okay, the meaning is modulus. This integral looks kind of innocent, but we want to find this definite integral for the limits, the fixed limits 0 to 2 pi, that full circle, for any value of a. I don't really know what a is. I'm just assuming it's either larger than 1 or smaller than -1. Okay. So okay. Let's convert this integral in this way. So how do we do this? Well, in this case, it's very easy. So the integral will be the contour integral over the unit circle of this function f. The function is 1 divided by a plus the sine of theta, but evaluated at sine of theta equal to z squared minus 1 divided by 2iz. Okay, and then we will have, let's do it like that, 1 divided by a plus z squared minus 1 divided by 2iz, and then we have to multiply by minus I over z dz. Right. Well, before we continue finding singularities, etc., we should simplify this function a little bit. Let's see. Let's multiply by 2z. By 2iz. Let's multiply by 2iz. The numerator was minus I. Minus I over z. So multiplying by 2iz, I get again 2 times I times minus 1, I times minus I, which is 1. And then we get z divided by z. And then the denominator will be a times 2iz plus z squared minus 1. Okay. Do you agree? How can we go from here? Well, notice that the denominator is a polynomial. It's a complex polynomial, but just quadratic polynomial. So this will be just 2 dz divided by, okay, let's write it like this, z squared plus 2ai z minus 1. A quadratic polynomial on the complex variable always has 2 zeros. Well, except if the 2 zeros are at the same point. In that case, well, it's very easy to remember. Either you have 2 simple zeros for the polynomial or 1 zero of order 2. That's the only possibilities for a quadratic polynomial of the complex variable, and it's very easy for you to check it if you don't believe me. So let's assume we have 2 simple poles for the denominator. Any question? So, well, how do we know we don't have one double pole, one pole of order 2? How do we know that this quadratic polynomial, z squared plus 2aiz minus 1, doesn't have a zero of order 2. You can just do it the same as you do it for the real variable. There is this discriminant. Probably you remember this, minus b plus minus square root of b squared minus 4ac. So here, what is b squared minus 4ac? It is 2ai squared minus 4a squared, and minus 4ac is plus 4. So this discriminant is exactly equal to 0, then the two zeros become 1, 0, 4. But this can only happen for a equal to 1, for example, or minus 1, or anyway, if a has a modulus larger than 1, this can never be 0. Okay, this will always have, this will always be larger, have a larger modulus. So we know, that's why we said modulus of a is larger than 1. In that case, we know this polynomial has two zeros, two different zeros, not 1 0 of other 2. But what are they? We don't even know a. So let's write that again. Z squared plus 2iaz minus 1 has two simple zeros. And let me call them one z plus and another one z minus, which you can take them with, as I said, with the normal equation. Just remembering that in the normal equation, we are kind of already taking the two possible branches of the square root, and the two possible branches are the plus and the minus of this expression that we have used since school for real numbers, right? For real variables. Minus b plus minus, okay, sorry, yeah, minus b minus 2ai plus minus the square root of b squared minus 4a squared plus 4a minus 4ac plus 4 divided by 2a. I mean 2. Sorry, not the a of this equation, but the a of. That's how I memorize it in school, and I still use this. Anyway, we can see the plus and the minus corresponding to actually the two solutions of the square root, which are the two branches of that function, will give me two complex numbers. Let's simplify this a bit. Here I can take these four out of the square root, and it will become a 2. So that cancels the 2 on the denominator. So we have minus ai plus minus square root of 1 minus a squared. Do you agree? And if I write 1 minus a squared as minus 1 times a squared minus 1, then I can take the square root of minus 1 outside. Okay. Okay, why do I do this? Because now it's interesting to see, remember, a is real. It's interesting to see that the two zeros of the denominator are purely imaginary, are I that multiply the real number minus a plus or minus the real number a squared minus 1 square root. which everything here is real because remember, a has an absolute value larger than 1. Okay, remember, we said this is larger than 1. That means the square root of a squared minus 1 is always a real number. And here we'll have a purely imaginary number for the plus and another purely imaginary number for the minus. But what do I get here? Well, let's write that again. The absolute value of a is larger than 1. That means square root of a squared minus 1 is, sorry, just one moment. Well, yeah, I mean, it's a number larger than 0. Okay, yeah, let's see. So let's see if I do let's see let's say the second case first. Is if I do this minus the square root of this, so you can see how this must be less than minus a, because, well, this number we already taking the branch, so this number is positive numbers. Here I have minus a minus another number. This would be smaller than minus a, and that means this number will have an absolute value. If a has an absolute value larger than 1, sorry. Sorry. If a is larger than 1, this will be less than minus 1. If a is smaller than minus 1, you can see that this will be larger than 1. That means the absolute value of this is for sure larger than 1. Why do I care about that? Well, because if the absolute value of that number is larger than 1, that number multiplied by I would be on the imaginary axis, but outside of the unit circle. Okay. So, well, maybe if you have 1 more minute, okay, 2 more minutes. I will finish this just for the example. So that means z minus, the modulus of z minus is larger than 1. That means this is outside the unit circle. As I said, the singularities that are outside of the contour give 0 contribution. Then it is possible to find that z plus multiplied by z minus is exactly equal to minus 1. Just take these 2 expressions and see what happens if you do sum times difference. It's the difference of the squares, and then you will get a squared minus 1 minus a squared, so which is minus 1. So that means the modulus of zeta plus must be less than 1, because remember the product of the modulus is the modulus of the product, and zeta minus has a modulus larger than 1. So that means there is always 1 outside the unit circle and 1 inside the unit circle. Even if we don't know the value of a, it will be for both cases. If a is larger than 1 or a is less than minus 1, z plus will always be inside the unit circle. So that means I just need to find the residues. So I need to find the residues of what function? Well, the function is this, well, 2 divided by this polynomial, which already includes the 1 over z. Actually, it even includes the minus I. Okay, sorry. So the residues of 2 divided by z squared plus 2aiz minus 1 at this point z plus, which is defined like this with a plus. We know it's a simple pole. So we know this would be 2 divided by, well, if you remember how to factorize, you will notice that the function, the polynomial, this polynomial z, I'll write it here, z squared plus 2aiz minus 1 should be the same as z minus z plus times z minus z minus, right? It's the factorization of this polynomial. So for the simple pole method in this case, this will be just 2 divided by z minus the other singular point evaluated at z plus. In other words, it will be 2 divided by z plus minus z minus. Okay, and we can just take the definitions from here. Z plus minus z minus, the minus ai disappears, and then we'll have 2 times, sorry, 2 times I square root of a squared minus 1. Whatever, I mean, this complex number depends on a, but whatever it is, you can substitute it at the end. And from the residue theorem, we just multiply. Okay, so I will just be 2 pi I from the residue theorem times the residue times 2 divided by 2a square root of a square minus 1. Anyway, we will get these 2 disappears, the I cancels, and then we get the integral should be equal to 2 pi square root divided by square root of a squared minus 1 for any value of a. Okay, so this was our first application. Thank you for your patience. Do you have any question before we disconnect? You still there?
Yeah, it's fine.
Thank you. Okay, do you feel yeah, you think you can try these? Well, yeah, I think the instructions are quite simple. So you will try these also as homework for another function, of course. Okay. And we will continue next week. Please check your email in also, well, for the homework and also for the next class. I'm not completely sure if I can do it on Thursday. So I will let you know by email, okay?
Okay.